Okay, I can start. Um, so thank you to everyone who's coming to this is our 11th speaker series for the Harvard Medical AI group. And today we have Yun Liu with us today. Yun is a senior staff research scientist at Google Research, and in his talk, he will first briefly cover his research journey and learnings in the medical imaging space, and then he'll discuss his research building AMIE for assisting with challenging clinical cases and tackling diagnostic dialogue, as well as results from early studies with patients. And finally, he'll share some of his work building and releasing LLM-based tools to enable others to build for their own applications. And after his talk, we will open the floor to discussion and questions. And yeah, I'll let you take it from here.
Good. Thank you, Stephanie, for the invite. Great to be here virtually. Um, I guess maybe a little bit about myself. I'm a scientist with the Health AI team here at Google Research, and I've been working in this space for a while. Before then, before this, I was actually at HST. So folks who are grad students at Harvard probably know about it. But it's a really interesting program that combines, I guess, a biomedical PhD program with the kind of like exposure to the clinical world. So I think in many ways it served me really well. So great to be back. Okay, so our team has over the last 10 years or so worked in a number of different areas. This slide is not to scale in terms of number of the real estate for each section, but it's really talking about different kinds of modalities and specific kinds of problems we've tackled over the years. Some of it deals with different kind of like by specialty, so radiology versus pathology and dermatology. And others here are kind of like based on specific problems within. So for example, prostate cancer, breast cancer, and so forth. The first part of the talk will deal with quite a few of these imaging-based modalities. And then most of the talk actually is going to be devoted to kind of like this section over here around generative AI. Okay, so oftentimes when I go to a biomedical venue, one of the first questions I get is, what is Google doing in this space? Why am I at that particular venue? And so I think our journey, at least our team's journey in this space, started a little bit over 10 years ago now. And in 2016, we published a paper that later on was named one of the 10 most influential papers of the decade by JAMA. This paper dealt with a specific problem. This problem was for patients with diabetes who are at risk of developing something called diabetic retinopathy or diabetic eye disease. Now, this disease is something that can lead to blindness if not treated. So one of the things you want to do to try and catch the diseases at earlier stages where it can be treated is to do eye screenings for patients. And so in this process, the way it works is that you sit in front of a camera. Oftentimes it's a desktop-based camera, so it's fairly large if it's on a table. And you can take a photo, and that photo can then be sent to a specialist for grading. If the specialist sees signs of diabetic eye disease, depending on how severe it is, it can then be sent for further follow-up. But essentially, when we were starting in that space, this was a few years after LXNet and kind of like the ImageNet improvements in performance. We're essentially trying to figure out a question, can we do something similar in the medical space? And turns out that these photos existed with several partners at sufficient quantities at a time to essentially brute force a number of labels and build a pretty good convolutional neural network based algorithm to detect DR in this case. So essentially, kind of like long story short, it worked pretty well. We published a paper on it. And then we eventually worked with many more partners to do more prospective validations and eventually worked with partners in India to launch this in real world screening. And since then, it's screened over 1 million patients. A few years ago, when it was roughly at the halfway mark in terms of the screening numbers so far, we did what we called a kind of like a real world validation or monitoring study. So what we did in that case was that we took all of the images that's been captured so far, and we did a bit of a random sampling of about 5,000 of these images. And those images were then sent to specialists to look over again. And we tried to capture what the performance was of those real world images. So no longer in a research study setting, but for patients who were actually using it for screening purposes. Sense and spec, so sensitivity and specificity of the algorithm in the real world cohort was over 96%. This was pretty close to matching what we had seen when we were developing the algorithm. And importantly, the numbers of severe plus disease, so this is the kind of like the severity of disease above which you need treatment, none of them were missed. Now, I'm not a marketing person, I'm not a salesperson, I'm a scientist. So when I see something that says 100% or 0%, I'm not happy, I get a little bit suspicious. In this case, what's happening here is that there's 5 grades of the diabetic eye disease, ranging from none, mild, all the way up to severe and proliferative. And so here what's going on is that essentially severe is the second most severe kind of like class. And for images that were severe, several of them were actually graded by the algorithm to be moderate disease. In this system, moderate disease is also referred to for eye care. And so what happened was that the grading did have a miss, but the actual kind of like decision making, there was no misses in that. So this paper was published in Dominant Network Open just last year. Now, at the same time that we're doing this work that was more about clinical workflows and helping with a specific screening problem, we were also working on trying to understand if we can do more with less. And one example of that was to look at these retinal photos and to see if we can get a sense of other signs of systemic disease from these photos. They say the eye is a window to your soul. In this case, it's a window to your overall health. And there are many things that you can tell from these photos. And so we did some work in that space. And then very briefly, we did a bit of work to try and help the, in this case, physicians understand the literature, the medical literature that was getting more and more of these machine learning related articles back then. Okay, and everything on this slide relates to fundus photos or eye images. We also worked with a number of other modalities. Some examples are low-dose CT for lung cancer screening, mammography, chest X-rays for just broadly figuring out if something is wrong, for tuberculosis, ultrasound, and a number of other things as well. And for each of these, I think we worked with partners that were very keen on bringing things forward. And some of them, we actually proceeded towards prospective studies with real patients as well. So this is going through kind of like a really large body of work by many talented people, like very, very briefly. But at the end of that journey, one of the things we were asking ourselves is, what does impact mean? I mean, for some of these things, we started to get towards prospective studies, which has really, really good evidence for understanding what has promise in the real world. And as we started to examine that question more closely, one kind of impact in our mind was really kind of like the diabetic eye disease related work, screening over 1 million patients, we thought was a really good achievement. At the same time, it's also just a drop in the bucket compared to the number of diabetic patients in India where this was being deployed. And so I think what that kind of like made us think really hard about is just, really inject a degree of humbleness to what we're able to do. And this took many, many years. And so for some of these things, we also worked with partners, recognizing that the partners are the ones that will understand their local jurisdiction and how to get things out the best. And for some of these, we've then licensed the models to the partners, and securing some commitments for them to proceed towards free screenings in their respective areas. Another example is to work with different product teams at Google. So we did some work in the dermatology AI space. And one of the things we then later did was we worked with this team that ships a product called Google Lens. Google Lens is supposed to be a visual similarity based kind of like app. So the kind of like the more typical use case is, let's say someone sees a car, a handbag, clothing, things that are sort of like visually visual based search. So they see that thing, they can't really describe it very well. Like you can say yellow dress or orange dress or something, but it's really hard to say, kind of like describe in, I guess, specialized keywords sufficiently that you get the exact dress. And so image based search has a lot of good use cases. Now we knew that people were trying to take photos of patterns, rashes, and other things that were appearing on their skin. But at the time, the app was not able to support this. So we worked with a team and incorporating some of the learnings that we got from some of our dermatology AI work, we help enable a similar image-based search experience for skin-related conditions. And what this really resulted in is the capability, it's available in the US, where you can take a photo of something on your skin, and it essentially shows you the visual matches that much closer. And this works a lot better than if you were to do just kind of like naive visual similarity based magic. Another thing that we started doing in this space was to start to release the models themselves to help developers and other researchers work towards it. And we'll talk a bit more about it later on in the talk. And I would say that Andrew also covered quite a bit of that in his talk a few weeks ago as well. All right, so that's kind of like concluding the part of the talk where I focus a lot more on our imaging related applications. And then the rest of the talk will be about generative AI. So I think most folks are going to be pretty familiar. I'm unfortunately in a version of Zoom where I can't see everyone right now, so I won't try to do an audience poll. But most folks will probably have used generative AI-based chatbots these days. And I think one way of thinking about this in comparison to the image-based work that we saw previously was that imaging-based work was you have image in and you have a structure prediction come out of it. Here, what you have is you similarly have a complex data type coming in. For example, text. It could also be images and other things. But the output of this is also complex. It's text, images, or something else. And so I think that kind of like from a machine learning perspective is the main difference between these two paradigms. Behind the scenes, what's happening is actually really simple at its core. There's lots of tricks you would do to kind of like making this work a lot faster. But at its core is doing autoregressive text generation. So getting a bunch of text in as a sequence and predicting the next element of a sequence, taking that as input again, and then repeating this many, many times to get a sequence generated. In modern times, and this is a little bit of an outdated screenshot, I guess, but in modern times, what you also see is that these models are doing what we call reasoning behind the scenes or thinking. And so what's happening is that instead of having a purely autoregressive text-based generation that's output is meant for the user to see, you also see that there's some tokens or text that's being generated that is not meant for the user's consumption. It's actually meant as an internal reasoning trace for the actual model. But then other than the stuff that's kind of like a thinking trace, you actually see the output that is meant for the user. And this is essentially a kind of like a inference time or test time kind of like trick to make these models work a lot better in some cases. So what do we do with these things? Well, I'm going to take a little bit of a step backwards in time to talk about projects that we first started working on before we've seen all of these fancier kind of like thinking-based models. So one of the first things we did in this space was to consider the problem, well, can these models actually understand enough medical information to be useful? And one source of challenging tasks for these models is to look at really reputable journals and look at hard clinical cases that they've put together. In this case, we looked at a New England Journal, CPC or clinical pathologic cases. And this is a case series where they've put together challenging cases incorporating the patient's history, labs, testing, imaging, and a number of other things that were done for the patient. And at the end, there's actually a final diagnosis. But the goal here is to present a lot of information such that clinicians can look over it and learn from that case as an example of in some cases, a very particularly complex diagnosis. And so what we did was to take these cases. At the time, this was a text input only models. We didn't use any of the images, just the text. We scrubbed out the final diagnosis and we fed that into the model as context. And the next thing we did was to ask the question, can we now take a model that's now seen this kind of like input and have it help a person actually get to a better diagnosis? And by a person here, I mean a clinician or primary care provider. So we did then a randomized kind of like study of these cases where there are two arms. In the first arm, there is a PCP that then looks at the case themselves. They first provide what we call a baseline differential diagnosis, so a list of ranked diagnoses based on what they think is most probable. They then are able to use an internet search. So they can go on the internet, look for stuff based on the symptoms or based on specific conditions that they're considering. And after doing whatever search they think is most appropriate, they can then update their list of diagnoses that they think are most probable. In the second arm, we have the first step be the same. They see the case and they provide a baseline, but then they get access to the AI that is prompted in this particular way with the case in the AI's context. And then they can ask several questions and then update their diagnosis if they would like to see. All right, and so what we're going to see in the next slide is what happens when we do the randomized study and what the results look like. So on this chart, what we're seeing is that list of diagnoses that they provide. If you go down the list from most to least probable, and you include more and more diagnoses, what is the diagnostic accuracy of the clinician, the person, as a function of the kind of like the final diagnosis. So if they capture the final diagnosis, then the accuracy is 1 for the example, and they can look at a percentage across all possible cases. So the first line here is the blue. This is the across the two arms when they're not assisted. So in this case, these two arms are basically identical because they've not done anything different yet. And we see that the baseline diagnosis for the first is actually pretty low at about 15%, and it only goes up to a little bit over 30% at the very end. The reason this is low is not because they were bad. The reason it's low is because these are challenging cases. Now, the next line over here is the green one. This line outlines what happens if they have access to internet search. And as you may expect, they get quite a bit of a boost here. And it's roughly speaking a 10% boost across the board, across this entire range of x-axis. The orange line is what happens when they have access to the AI. So this is built off blue to orange and blue to green. And this orange line you'll see is kind of similar in the first couple of positions, but then it widens the gap towards the end. So what we're seeing here actually is that these PCPs in this particular arm are getting some benefit out of the AI assistance, such that they are lengthening the average length of their differentials. And after lengthening it, more of the correct answers are actually in the slightly later positions on average. This is why a lot of the gain is coming in more towards the end. Now, the elephant in the room is the red line over here. And what we're seeing in the red line over here is it's higher than any of these, both the unassisted kind of like clinicians, but also any of the assisted clinicians. And again, though, we'll see that a lot of the benefit and the gap here is coming in more towards the end. So what's the takeaway here? Well, I don't think the takeaway is that the red line is the highest. I think the takeaway here is that AI is clearly able to draw associations between complex medical information that's provided in the context, and from there draw the right associations such that it's understanding which diagnoses are most probably associated with these symptoms and case presentation. And the assistive part of the conclusion really is that if you have that assistive capability, the kind of like the PCPs are actually not getting significantly better at differential diagnosis because they're getting a lift in this particular scoring. Okay, this study so far, all it's shown is that there is essentially a big blob of information that's given to the AI, and the AI can then use that to assist a physician. But in real life, that blob of information does not usually exist right up front. Patients will never come into a clinic and talk about all the symptoms they have, and somehow magically have all of their test results and so forth. What's happening in real life is that the physician has to talk to the patient, figure out what it is that's wrong with them. If they don't ask the right questions, they're not going to get the right answers. You're going to be pretty limited if you just rely on essentially what the patient is able to tell you without further prompting. And so one of the next things we try to do in this space is to figure out, can we try and test for that capability as well? Can we have the chatbot ask the right questions to the patient so that they can then get the right answers and then arrive at hopefully the right diagnosis? So this was a little bit a few years ago. And so the models at the time, we actually did some amount of tuning to get them to be more conversational and to ask the right questions. These days, this kind of like capabilities is a lot more integrated into the AI, and so you may not need to do that quite as much. But essentially, what we did then was to train it to solicit the patient's history in a conversational way, and then we did a similar kind of randomized study. But this time, what we did was to work with patient actors because you need a something to be playing the role of essentially the fake patient. In this case, these are professional patient actors who essentially usually participate in training medical trainees. And so these patient actors are given a scenario that they then act out. And if the agent that they are talking to do not ask the right questions, they're not going to be proactively necessarily offering up the right answer. And then the agent that's being tested would then score more poorly. Behind the scenes, what's happening is that sometimes they're talking, this is where the randomization comes in. Sometimes they're talking to a AI agent, and sometimes they're talking to a primary care provider who behind the scenes is a real human person that is typing into the chatbots. One limitation here, I would just say upfront, is that because of kind of like the desire to go blind this study so that the patient actors didn't know who it was they were talking to, also because the technology was more mature in a text space, all of this work was done using a text-based chat interface. And this means this is not really representative of how most people seek medical care. Most people are not talking to a doctor via chat. Right, so what's the result? This plot is very, very similar to the previous plot with the same axes as before. One thing you will notice is the y-axes here are a lot higher numbers. Part of the reason why is because these were based on scenarios that were created that were meant to be pretty representative of real cases. So not the most challenging cases that appear in a journal, but kind of like more normal everyday cases with a bit of a spectrum in terms of difficulty. And what we see here is that the primary care providers, remember the patient actors are blinded. The primary care providers, kind of like that arm, their differential diagnosis accuracy is ranges from about 60-something% all the way up to about 80-something. And the red line over here is for the AI, essentially talking to the same patient actors, was quite a bit higher, about 10+% higher across the board. The other thing that jumps out in terms of results is that we saw pretty high patient actor rated scores for empathy and communication. And that's on this plot here, this particular axis here. This is where you see one of the bigger gaps. And probably the reason for this gap is because when an AI chatbot is presenting its outputs, it doesn't get tired. So it's able to kind of like present results in a really nice way and sometimes kind of like a longer response. And this is correlated with, I guess, perceived empathy. All right. So those results that we just looked at were essentially based on scenarios that were created to be fairly representative of a broad range of scenarios. We've also worked with several collaborators in different institutions to understand what happens in more subspecialty-based areas, cardiology, oncology, ophthalmology. And for each of these, we have an associated report that you can look at if you are interested. All right. So far, I think most of the work that we've looked at are kind of like what we think of these days as more traditional AI, where there is a chatbot-like system that someone is talking to, whether that someone is a patient actor or a physician. As we started proceeding more towards kind of like more recent work, we started to essentially make it more agentic and a little bit more complex behind the scenes. And the reason for the complexity is so to enable different kinds of capabilities that doesn't natively work really well if you just have one single AI agent that is talking to the person and nothing else. So one example of that increased agentic sort of behavior is that we can have a fast language model that's having the actual conversation with the patient. It updates an internal state. That state is referred to by a separate agent, and that agent then goes off and looks at, in this case, medical guidelines to figure out which guidelines are most applicable, drafts up plans, and does other stuff behind the scenes. And it updates kind of like the plan and the state and everything else at some kind of interval, such that the fast agent that is talking to the patient then has access to the best information. So what this does is that we're looking at these guidelines. It can be something of a more of a computationally expensive process. And so by making this kind of like two separate agents, you can make it essentially leverage the fact that you can have something that needs more compute and more time to happen behind the scenes, while the agent that is talking to the patient is still able to do this kind of like low latency, high turnaround kind of like task quickly. So that's one type. Another type is something that kind of like another type of technical innovation here involves kind of like incorporating insights from human-computer interaction. So if you think about the last time you visited a physician, it's probably likely that the physician had many more questions for you earlier on in the conversation, where they were trying to figure out what happened to you, what your history was, and so forth. So there's a lot of information that was on average flowing in one direction, meaning from the patient to the physician. Later on, as the physician gets a better idea of what's going on and they come to their own idea about how to then manage it, that information flow may then potentially revert, such that on average, there's more information flowing from them back to the patient. And this is kind of like similar to a state-based system. We can think about it in a simplified way. It's a state where you're taking the history initially, figuring out a diagnosis, and later on you're kind of like conveying information and answering questions from the patient. So here, what we did was to then explicitly build that into the system, such that the system was essentially only moving on to the next step after it's certain enough. And what this does is it helps you essentially make the agent behave in a much more well-structured way by design. I would say that there are some downsides to doing this. So, for example, if you proceed from history taking to getting a diagnosis, and the very last step you go like, okay, and then you should be taking this antibiotic. And the very last step after you've sort of made the decision in terms of your state flow, the patient says, well, actually, I'm allergic to that, right? So there are certain cases where not having such a structured unidirectional only flow could be quite helpful. And so in some cases, you do want to make sure that there's a way that the agent can recover from that state, whether by moving back or by revisiting things or so forth. So some flexibility is definitely needed, and kind of like a fully unidirectional state-based system is not always ideal. All right, so all of that was in the research realm, and this is as well. But then the next kind of like thing that we did was to try and figure out like how would we potentially operationalize this in practice. And one sort of like conceptual way of doing this is to think about as the information is flowing from the patient to the physician in the first part of the conversation, there's actually not as much risk happening because that's mostly, for the most part, information extraction from the patient. If you think about where there might be risk, that risk may come in only when the AI is providing information back to the patient, and some of the information may be wrong or so forth. So if you think about that as sort of like a phase system where information collection is fairly low risk and information provision potentially may have higher risk, you can think about, well, can we guardrail the system to do just the first step, but then have human oversight over the second step? And so this kind of like paradigm is what we call the guardrail system, where essentially kind of like in the initial phase, there's the AI information extraction, and then there is physician oversight over the plan that the AI has before that goes back to the patient. And so that's what we outlined in this particular study. And we did some work to see if the AI will perform similarly to primary care providers or nurse practitioners who are asked to do the same kind of task, essentially as acting as a guard-veiled kind of like agent. One interesting thing in this space, if you look at the paper for more details, is that we found that primary care providers were actually worse than nurse practitioners at this kind of like guardrailed kind of like role. And part of that is because their training and their day job is actually not to remain guardrail. They are providers. They're able to provide such information. And so I think, or at least we think that the reason we're seeing kind of like a difference in the behavior and what we're measuring is just because of their inherent kind of like jobs and what they're usually trained to do. Okay, so how do we think about impact in this space? Well, I think at this stage, a lot of the impact in this stage is really to share the knowledge, to do the studies, the research studies, and then share the knowledge with the world, and to progressively move from more retrospective and simulation-based studies towards real people and then real patients eventually. One of the first things we did, and we just released this preprint, I think about a couple of weeks ago, was a collaboration with the Beth Israel Hospital in Boston. And this involved about 100 patients for kind of like a feasibility study to understand if it's safe potentially to use such AI system for real patients. So recall that the previous slides dealt with patient actors in a kind of like a retrospective study. So the patient actors were enacting scenarios. These were not their real kind of like concerns. And so there's no real chance that they will act on any information that they're learning because that's not their concern to begin with. Here in a prospective study, what we did was to study real patients who had real urgent care visits and giving them access to the AI to kind of like have a chat and then to see if those chats were actually safe. All of the chats were supervised in real time by a physician who essentially were on a video call at the same time as the patient using the AI. And one of the primary things we were monitoring is whether the physicians that were supervising the interaction felt like there was a need to stop the conversation at all. Fortunately, there was zero safety stops. This is another instance where I think zero is an indicator that the rate is probably very low, not that it is truly zero, because this was after all 100 patients. So it's kind of like when the estimate is zero, it's really hard to create a confidence interval of it. But what we did observe was that there were no issues with safety in this particular study. We also saw that patients were largely very satisfied with the study. Another encouraging sign is if you think about kind of like the patient attitudes in terms of how much they trust the AI and also a few other kinds of questions. We saw that in general, they before versus after using the AI, they actually trusted the AI more. Another thing we did in the study was kind of like a similar analysis you saw previously, where the x-axis is the length of the differential diagnosis, and the y-axis is the diagnostic accuracy. And we looked at the AI's accuracy, and it was actually pretty good and somewhat comparable to what you would see from a provider as well. Now, finally, the last piece we looked at was the management plan by the primary care provider versus the AI. And in a blinded side-by-side comparison, other physicians judged them as being overall fairly similar, statistically no different. Okay, so that was a single center study in Boston. And what we are now moving towards is a kind of like a larger scale randomized study with a telemedicine partner. And so this study has been announced, but it hasn't started quite yet. Okay, so I think everything we've discussed so far is kind of like, if you think about the application, fairly specifically focusing on a patient's journey through a healthcare system and them talking to a doctor and trying to understand what role the AI can play in that kind of a end-to-end clinical journey. Another set of things that we do are really around exploring what the capabilities are of AI, just kind of like more broadly speaking. First couple of slides I'll probably go through a little bit more quickly because it's older work, but I'll highlight a few things that I think are interesting and still relevant even today. So for those who are monitoring a little bit through kind of like the progression of AI and natural language processing, in the medical kind of like realm, may remember that kind of like similar to how ImageNet was a challenge that people were monitoring performance on, that there were certain benchmarks that people were trying to use to understand the capabilities of these models in this space. And one such benchmark is it's a popular one called MedQA. These are medical exam licensing style questions. And if you look over time, and this is time on the x-axis, you'll see that there was quite a bit of a jump around late 2022 or so, where the models get much, much better. This was also around the time that we started working in some of this space over here. And then later on, you see that it kind of like slows down. But the reason it slows down isn't so much because there's kind of like the models weren't getting better, but that they were starting to approach kind of like they were saturating this benchmark, essentially. Another work that we did in this space kind of like fairly early on, this work that we call MedPOM-M, this work really tried to figure out if the text-based models back then could then handle multiple modalities. But specifically, we wanted them to handle multiple modalities using the same kind of encoder. And the reason this was kind of like interesting at the time was because prior to that, I think almost everyone was trying to see if you can get in order to handle a new modality, you'd be training a new encoder to handle that modality. And so in this experiment, what we then did was to say, hey, there's only one encoder. Can it handle all of these different modalities all at the same time? And it turns out it can. It wasn't quite performing at state of the art for everything, but it was performing pretty decently at everything. So that was kind of like a interesting milestone in some of our work. The other thing we did here, this is a project where we were examining for issues of bias and equity in these language model outputs. And here, I think one of the main lessons or useful takeaways here is that we realized that if you ask the same question to different kinds of people, they'll have different answers. And by that, I don't mean inter-rater variability as you classically think about it. But what I mean is if you ask about issues about bias and equity to let's say a layperson, versus to an equity expert who's thinking about social factors versus to a medical person who's thinking about risk factors in the medical sense, the way they think about bias and equity factors are quite different. And so they rate things very, very differently. And so I think my takeaway here is that if we look at kind of like reports, now going forward or in the past, about kind of like bias and equity aspects about many of these models, it's probably useful to look at who they had doing these ratings, because depending on who they were, the way they rated and what they flagged as issues may be quite different. Okay. And then slightly more recently, this is timeline-wise actually pretty close to some of the work we saw in the previous section. We were looking at them building on what was then the latest versions of the Gemini models to try and understand their potential for various kinds of medical tasks. This was divided into two reports. Very briefly, the two reports, one of them focused on broad capabilities for text, for using tools such as search, for understanding videos, and all of the medical modalities in terms of medical imaging and other things were in the other report. All right. So switching gears a little bit in terms of the capability space, another thing that we did in this space was to understand if we can leverage data from wearables that people oftentimes have on their wrist or on their fingers. And these wearables, really what they have for the most part are things around kind of like PPG-like signals, so around waveforms of the blood coursing through the body, as well as accelerometers and other signals. But they're pretty rich in terms of understanding what a person is doing, how they're moving in the course of a day. And so the question was, can we leverage these signals as some kind of passive indicator of health in ways that can be really helpful in managing people's overall health status? And so very briefly, some of the work here that we involved focused on activity and sleep, because these are things that are very much correlated with the way a person moves and how active they are. And then later on, we did a bit more of a broader take on kind of like overall health management and what people want to do in a perfect world. One thing that's a little bit interesting and maybe useful for folks here is the concept of something called a critical user journey, or CUJ. So a CUJ is essentially a fancy way of asking, like, what do people do with a potential feature or product? And can you thematically group them into different groups? So here what we did was to collect a number of different use cases across various channels and then cluster them into different kinds of CUJs. Based on those CUJs, that much smaller number of CUJs, we can then design a system that meets these CUJs based depending on which agents are required for each CUJ. So I think in an upshot, in kind of like in summary, this is what the main part of the work was about. All right. The other part to the wearable data space is that much of wearable data is being sort of like collected fairly continuously. So you have these signals where, let's say, you have a light sensor that's shining on the wrist, and you get a sense of how the blood is flowing. But the sensor data is actually a little bit too dense to analyze directly. So oftentimes they're summarized as kind of like average heart rates, resting heart rates, and that sort of thing. And so one thing that we then try to do was to ask the question, can we model the complex dynamics in these raw signals in a much more complex way and get much more useful information out of it? It turns out it's pretty hard to do so, as you can imagine. Anyone that's done experiments with real signals would know that real data is pretty noisy. But it turns out that if you train these models in the right way, you can get an encoder that understands the complexities of real data pretty well, such that you can then take the output of the encoders and do various useful predictions. And we have certain the number of different papers in this general space here. All right. And so how do we think about impact in this space? So the first couple of slides in this section, I talked about language models, and I think a lot of that impact is really related to both the example on the AMIE and the AI for kind of like patient care journey space, but also for some stuff that I'll talk about a little bit later in terms of the open models. But the other thing that we really think is useful here is to figure out what are useful for the everyday user. In terms of a personal coach or personal health assistant that they can have on their wrist that understands what's been going on in the course of their day and can then help them. And this can be used for kind of like general wellness. And so this kind of like overall concept is something that we are building towards. And I think some of the early releases or previews are coming right up. Another thing that we did very briefly, and this is the very last link on this slide, but it's a lab called a Plan for Care lab. And what this lab does is that it helps people prepare for a doctor's visit by really trying to get them to go through kind of like a symptom, collecting all of their symptoms, summarizing it potentially for the visit, but more importantly, helping them prepare for the visit by figuring out what questions they should have for their physician. And what we hope this will help really do is to help people have much more productive visits when they're visiting their provider, and just to really help them arrive much more prepared and, if needed, to advocate for themselves better. Okay. So the last part of my talk, and I'll keep this much briefer, just because you guys had a talk about this a few weeks ago. For those who are not at the talk, I think you can check out the YouTube channel for the HMAI group, and I think Andrew's talk is already up there. So I'll keep the this part of the slides, at least the parts that I think he's already talked about, to be fairly brief. So very briefly, what we've been doing in this space is to figure out how do we enable the community to build towards kind of like AI in healthcare a lot more easily. And one of the things we thought was very helpful is we can essentially create foundation models that people can fine tune for their own purposes. And one of the things that this enables is that it makes collaboration a lot easier, because then you can bring the model to various places where the data exists, as opposed to trying to figure out how to share data, where in some cases can be quite challenging. So I'm going to skip this fairly quickly. And some of the models that we're releasing in this area include NEJM, which was the focus of Andrew's talk. And alongside NEJM, the image encoder associated with NEJM is MedSiglip. And with a few kind of like very slightly older models here as well for chest x-ray, dermatology, and then one for audio as well. One thing that's missing, I think, from this slide is a medical transcription model called MedASR. This slide, I think, was in Andrew's talk as well, but very briefly, it covers a number of different modalities. And I think the our mental model here is that we would love for this to be something that people kind of like start off with and really fine tune for their use case, doing their own validations as needed to figure out what's feasible and what's not. And I'll skip this slide very briefly, except to say that it does permit, it's fairly permissive in the kind of things that you can do with it. Okay, I believe Andrew had some demos, so I'm going to skip these couple of slides and go straight to something that I think is a little bit newer compared to when he was speaking. So how we think about impact in space is really people taking the models and the tooling that we've been building and then starting to use them. So one of the initial surprises, and apologies to folks who were at Andrew's talk, he talked about this, but one of the initial surprises in this space was when we released MedGemma, the first version around mid last year. And about 10 days or so after the model was released, someone came to the forums and dropped a note there that took us a little bit by surprise. The note basically said, thank you for releasing NEJM. We've incorporated it into our application. It worked great. And we were just taken aback a little bit because, like, how can you do something in 10 days? So it turns out that this particular team, they have something called an Ask CPG application. This application is used to query clinical practice guidelines in their local system, in this case, Malaysia. So the way it works is that Malaysia, in this case, had about 100 or so of these clinical practice guidelines, and they wanted to enable people to ask, to essentially query those guidelines in natural language. So they would have a text-based stack where people would ask questions in text, and there'll be a query that's run, and the answers come back grounded in kind of like the clinical practice guidelines that exist in Malaysia. So what they had done essentially was that they took their existing text-based stack, and they knew that they wanted to enable a use case where people can upload images and query that same corpus. And so they took NEJM and they fine-tuned it for a captioning task, meaning that the images that were uploaded were captioned by NEJM in their fine-tuned version to, let's say, describe what the properties of the lesion were, and or to add more essentially possible conditions. And that text-based caption then goes back into a text-based stack to then essentially continue that journey. So essentially what they had done was that they had a text-based kind of like application, and then they used NEJM to enable the multimodal part of that workflow. So it's pretty impressive they were able to do that pretty quickly, within about 10 days to 2 weeks from release. Now, the other thing that we did, we started earlier this year, timed with the release of NEJM 1.5, was that we started a Kaggle challenge that was about 6 weeks in duration. And we invited people to essentially try it out and show us cool concepts of what NEJM could do. And when it first started, we were a little bit taken aback when about almost 7,000 people kind of like registered for the challenge. And we weren't sure who could essentially handle 7,000 entries. It turns out that later that over 1,000 people did end up submitting, and these form about 850 or so actual submissions. And this all happened in about 6 weeks or so. So the challenge closed about a month ago today. And this morning, we actually released the results and the winners of the challenge. So for folks who are monitoring the system, that would then show up. These are the 4 winners. I'll just play a couple of them to get a little bit of a flavor of what they're about.
Every week across West Africa, community health workers see patients with
Is the audio coming through? Okay, so I'll
fevers,
let it play for
coughs,
a little
and
bit.
NEJM 4B, the potential worker in Dakar, Yoruba, see counts, syndrome breakdowns, and recent cases color-coded across 11 WHOIDSR syndromes. When any syndrome exceeds its 4-week baseline, EPICAS flags it as a potential outbreak so officers can investigate before it spreads. For weekly reporting, NEJM 27B generates situation.
Okay, so pause there a little bit and let me skip back to a little bit kind of like where they were earlier. And so this concept essentially had, and this was one where the developer had gotten a data set of multiple African languages, and it had tuned NEJM to ensure that it's able to extract information from those languages fairly accurately. And what this concept then does is that its goal is that community health workers and other folks who are on the ground are able to log information about diseases into an app using a natural language-based input. The app then offline is able to extract information from that free text, and that structured information is in a format that's compatible with centralized reporting. And whenever it has connections, it can then upload the information to the centralized kind of like reporting. And so that can then be put on a map as a dashboard and other things to monitor for possible outbreaks. So what's interesting was that they were able to essentially do all of this tuning, all of this mocking and everything else, essentially within the course of the hackathon. This was the first place winner. I'll play the next one without audio and skip around a little bit.
More specifically, the
this was
beautiful
one.
Burley Beach on Australia's.
This was one where the submission was
Gold
about
Coast.
Australia
Now,
and
Australia's
their.
known for its beaches, known for its sun.
It was about Australia and trying to help with skin screening in Australia. And so what the app actually does is that the concept is that one can take a photo of the skin, and the app is then trained to essentially generate clinical descriptors of the skin. So you can imagine things like maybe properties of that particular lesion, whether it's erased, what color it is, and whether the borders are asymmetric and that sort of information. And by generating that, it can help essentially flag when things might be not great, and then encourage the person to then go in for a skin screen. So this is kind of like the one of the other entries as well. So you can see a couple of these mocks that they have here. The other thing I would say is that the production quality here is actually quite impressive in terms of the concept that they were showcasing here as well. And a few other entries were also really impressive. This particular slide has a top 4, but they're all featured on the winners list as well. So in interest of time, I'll skip to the next slide.
Hi, I'm
And this slide kind of like outlines that there were a few what we call special prizes that were awarded during the hackathon as well. And these special prizes really center around 3 main themes. 2 of the themes were agentic prizes and novel tasks. And by those, we kind of define as agentic workflows. And novel tasks are things where the NEJM kind of like initially released model was not optimized for a certain thing, and they figured out ways to make it support other things. One example was them hooking up to a segmentation model to do the segmentation and combining that with NEJM essentially to make it capable of segmentation, but also using the segmentation information in various ways as well in the workflow. The Edge AI prize went to essentially someone that had a specific use case that was quite compelling for offline use, where they took the smaller of the measurement models, the 4B model, and they ensured that the model essentially can query also clinical practice guidelines, but can do it in a local way, with some of the goals being to be able to support community health workers with not so great internet connection. And partially this entry was also inspired by disaster areas where the connectivity and other things may not be very good at that time. I'm going to try and advance to the next slide, and let's see
Medical
if it tries
expertise
to
is
play
unevenly.
all of the videos. It does, so let me try
Yes, man.
this.
So whopping 1.9.
Okay, there we go. All right, so this is my last slide. I'll take some questions. So very briefly, I think the work that we've done so far, we focused a lot of efforts on computer vision initially, and we found that computer vision algorithms can be quite helpful in certain healthcare settings. We've managed to get some of these off the ground and together with partners screen over 1 million patients. For generative AI, it's I think still a fairly young field, but it's maturing pretty quickly. The capabilities are advancing very fast, and so we're seeing more and more things that one can do with it. And some of these involve conversational agents, and some involve multimodal work. But I think we're pretty excited for the things that we're seeing people build out of it. We ourselves have explored many things, ranging from patient-physician kind of like conversations and journeys, to supporting patients in between kind of like visits in their everyday lives. And we're also releasing some models for everyone else to use as well. And we're seeing some really interesting stuff that people are doing with it. Now, if you're interested in following our work, the left QR code goes to our Google Scholar page with all of the papers. There's about 300 of them, so don't rush to read them all. The right side QR code goes to the open models that Andrew and I were talking about, so feel free to check it out. So with that, I'll conclude the part of the talk. I'm happy to take any questions.
All right, thank you for this really informative and amazing talk. Yeah, we'll open the floor to questions. So if you have questions, just raise your hand and I can unmute you and you can ask your question. But I'll start off with a question. So out of all the projects that you've mentioned going forward, which one are you personally most excited about?
Yeah, so I think I'm excited about a number of them for different reasons.
Mhm.
I would say that we are working on things for specific purposes, including the kind of like helping patients through various parts of their journeys. And I think that's exciting from a what we are doing perspective. The open models and enabling a community, I'm really excited about it because I think there's many more people out there than there are on our team and in our organization and our company. And I think that it's really the community that will kind of like be building some of the most amazing things for their own particular use cases. So I'm really excited to see what people can do with these models. And as the models get more capable, and you have models that can help you build more models, especially, then this will, I think, just accelerate, if anything.
Yeah. And if anyone has any questions, please raise your hand. Let me see. Okay. Let me unmute. Siavash, are you able to
Yes. Can you hear
unmute?
me?
Yes.
Perfect. Thank you so much for this presentation. I've been following a lot of the work being done by your group for a couple of years, and I think it's really cool. Um, I was curious if you could if you could elaborate a little bit deeper in terms of like sort of some of the final performance metrics and capabilities. How does MedGemma compare to something like MedPalm in that regard? And do you have plans to continue working on MedPalm in the future?
Yeah, that's a great question. For good or bad, I think there's been some branding, whether for research purposes or other things, of each kind of like stage of the work. It makes it much easier to refer to when you're writing a paper. To instead of saying like our model, this AI, you're able to refer to it as something. So that branding does happen. MedPalm was built upon a family of models called PALM, so pathway language models. This set of models was superseded by the Gemini models. So the current kind of like best in class models that Google has is the Gemini kind of like family of models. So to the simple answer to your question is like, no, we're not currently working on MedPalm, mostly because work has shifted to Gemini. There is some work that landed in something called MedLM. This was the kind of like the commercially available version of some of the MedPalm based models. And behind the scenes, they were kind of like developed such that they were meeting needs that we felt like the people were coming to Google and cloud for. Those models have since been replaced by Gemini as well. And part of the reason is that we essentially do these kind of like benchmarking and other things like all the time to measure the quality of the models that we have and the capabilities. And so essentially what we were finding was that a lot of the more recent general purpose models were starting to outpace the performance of these medical specialized models at a time that we're putting out. And so if you have kind of like model generations that are evolving every half year or so, or every year to half a year, then kind of like the general model starts outpacing that specialized model performance, because the specialized model is sort of like frozen in time at a time that you did that tuning. So in those cases, that's been superseded by the general Gemini models. For MedGemma specifically, I think one thing that it's like much better as a base starting off point compared to Gemini 4 right now is that it's much better at understanding medical imaging. And part of the reason is because you look at these general purpose models, they're meant for general purposes, and the kind of like the language that people use in the medical world, there's some differences, but it's still kind of like language that kind of like people sort of ish understand for the most part. If you think about images, though, the images can look very different than anything the everyday person is used to seeing. And so MedGemma has been tuned such that it understands medical imaging like a lot better than kind of like a general purpose model does. So I think there you would see a much bigger gap on average.
Okay, thank you. And then we have a question in the chat um, from Afaf. Do you think we still have a lot of technical gaps when it comes to computer vision research in cancer diagnosis? Or is it all about who has more newer data now?
Yeah, this is a great question. So I think you can approach this question a few different ways. One is kind of like, what are gaps in getting performance up the highest? And maybe I'll focus on that again, kind of like chime in and tell me if there's something else you're thinking about. So I think if we look at the per application state-of-the-art convolutional nets, some of the more recent models will, be comparable, I think, performance-wise, some a bit better, some a bit worse than the best-in-class convolutional nets. So I think a lot of it, in terms of the algorithmically, we were pretty much there, given a particular kind of like data set and problem definition and so forth. I think there are still gaps, though, in terms of like, if your ground truth is based on like human labeling with enough data, I think in general we see pretty comparable performance and very high, like in the 90s or higher performance by AI. When the ground truth is something that's more related to outcomes or from a biopsy or some other information that a human can't see, I think that's when we're seeing a little bit more of a gap. I think part of it is because the original input may not have all of the information required to get to as high quality of a label as the ground truth they're comparing it against. So some examples are, if you look at a skin image, but ground truth is based on biopsy, that's just in general a hard task. If you have a mammogram input and your output is whether they get a diagnosis of breast cancer in the next 3 years or something, including interval cancers, that's a harder ground truth. And so it really depends on what ground truth you're looking at. And if the ground truth is not just based on human labeling, then oftentimes there is a little bit of a gap just because the task is a lot harder.
Thank you for that. And then we have another question from Andrew. Andrew, if you want to ask your question.
Thanks for the super interesting presentation. I'm wondering, now that you guys have a couple years of experience running AMIE and its pilot studies or this upcoming included health study, do you guys have an opinion of how it will fit into physician workflows in the future? Like, will it be a tool that patients use when they check in before they talk to the physician? Or will maybe patients even be able to use it outside of the physician context? Just curious how that interacts with regulatory things and what you guys have learned about that.
I think if this were a multiple choice question, I would check the all of the above box, I think, for this question. I think it's kind of like what you actually use it for probably depends on the specific workflow you're targeting and what is more versus less launchable. I think stuff like maybe helping getting information before kind of like the guardrail concept that we had in one of the research papers. That's something that likely will be easier to get out the door. Maybe, and this is not something we've worked on yet, but maybe if you have something that's like collecting patient sentiments or something like a survey kind of like thing after the after a visit, but instead of doing it in a structured survey with a few boxes, it's more engaging. It's a kind of like a language-based chatbot. Then that kind of stuff is probably more easily launchable. You have something that's like fully autonomously somehow doing all of the work that a doctor should be doing, then I would assume it's much harder to launch for various reasons. So I think it really depends on the specifics. Some things are going to be easier to get out the door. Some things are going to be much harder. The safety profile and the kind of like consequences of something going wrong for each of these workflows is also a little bit different. If you're asking a survey and collecting information, it's probably pretty low risk. If you have something fully autonomous, then depending on what exactly it's doing, there may be some more risk.
And then we have time for maybe like one or two more questions. Arnita, if you want to ask your question.
Yes. Hi, Yun. Thanks for the presentation. Always been a fan of your work. I guess this is a question of out of curiosity. With Google Health AI enabling more downstream creation or development of models with your open source. I'm just curious, what would be your vision? What would be your success metrics with having this open model available, and what do you envision for the world to be in the next 5 years with this enablement now? I'm just curious.
Yeah, that's a great question. If I could just sort of like wish for anything, I think I would love it if folks were able to build upon it, basically wherever they are for their workflow. I would also be really excited if there are ways where people can share that progress more. And by share, I don't mean kind of like publish on it. I mean that kind of like hypothetically, if you think about everyone building their own model, that's all, kind of like, let's say, based on NEJM. And we know that models tend to, on average, get better if it has access to more data and various techniques. Are there ways where people can share these things in certain ways? So it's not just kind of like individually tuning for their use case, but somehow benefiting as an overall network is the wrong word, but kind of like network, by the fact that everyone's starting off from the same models. I'm hopeful that eventually we kind of like try and get there, just because, we would like people to use it. We would like people to benefit from it. We would also like everyone to be able to benefit from each other's data and progress, if there's a way to do so.
All right, in the notice of time, we are a bit over time, so if there are any questions, is there any other way for them to reach out to you to ask questions, or
Yeah,
are you
feel free
okay
to
with
reach out
saying?
on LinkedIn.
Okay.
Yeah, LinkedIn's great. It's probably the easiest. And I think some of you, I think I'm already connected with, so feel free to just send your questions over.
Great. Thank you again for taking the time to share your research today, and thank you to everyone who took the time to come to our speaker series. And this video will be posted on our YouTube channel afterwards, so make sure to check